All right, let's jump right into this explainer. We're going to explore the incredible technical challenge of containing forces that can, well, literally shatter stone. When we talk about modern energy infrastructure, we're really talking about pushing the absolute limits of material science. So today, we're focusing on exactly what it takes to maintain the mechanical integrity of equipment that's operating under just unimaginably extreme conditions.
Picture this. Imagine the wellbore as a high-pressure pipe in a massive hydraulic system, but one that is buried miles deep beneath the Earth's surface. Up here on the surface, keeping a hydraulic line intact is fairly straightforward. But down there, this steel pipe has to withstand immense geological pressures, extreme temperatures, and volatile dynamic loads, literally all at the exact same time.
Here's our roadmap for today. We'll look at the confined pressure challenge, define the fracture gradient, talk about the critical cement sheath, cross the yield point, look at dynamic loading and corrosion, and wrap up with the engineering precision paradigm.
First up, the confined pressure challenge.
Now, the entire goal of this system is to interact with the rock formation, right? And that requires an intentional vulnerability. During operations, the steel casing undergoes what we call perforation. This is where the casing is deliberately breached using shaped charges to allow high-pressure fluid to access the reservoir. By intentionally punching holes in our own armor, we're inherently testing our limits and pushing this confined pressure system to the absolute extreme. And because we're forcing fluids through these perforations at such incredible pressures, there is absolutely zero room for error anywhere else in the pipe. If that miles-deep steel casing has a single microscopic defect, maybe a tiny weld flaw or a patch of early corrosion, it acts exactly like a sharp corner in other machinery. It dangerously concentrates stress right at that microscopic point. Under thousands of pounds of pressure, that tiny stress concentrator is exactly where a catastrophic structural tear is going to begin.
Moving on to number 2, defining the fracture gradient.
To really grasp the sheer scale of the geological forces we're fighting against, we have to look at a fundamental concept, and that is the fracture gradient. Simply put, this is the exact pressure threshold required to literally break the surrounding rock formation. We aren't just holding pressure inside the pipe, we're fighting the rock itself. The fracture gradient dictates the absolute limits of an operation. It completely determines the weight of the drilling mud and the fluid pressures you need to safely induce fractures in the rock without accidentally tearing the entire geological formation apart in ways you definitely didn't intend.
So engineers use complex geopressure predictions to navigate what they call a narrow drilling window. Honestly, it's a super high-stakes balancing act. Exceed the fracture pressure limits and you break the rock unintentionally, causing complete fluid loss right into the formation. But if your pressure falls too low below that window, the massive weight of the Earth just collapses the wellbore entirely. You are quite literally threading a needle miles underground.
Which brings us to part 3, the critical cement sheath.
So how exactly do we structurally defend against these immense geological forces? Well, it isn't just about the steel pipe. The difference between a perfectly centered pipe with an even ring of cement, what we call a 100% standoff, versus an off-center pipe with a 10% standoff is huge. When hydraulic fracturing occurs, that improper 10% centralization causes a massive, dangerous stress spike on the casing, actually increasing the stress on the steel by over 140%. That is a massive difference.
A lot of folks don't realize that the cement isn't just glue meant to keep things stable. It's actually, arguably, the most critical part of the well's safety system. It forms a sheath that acts as a vital shock absorber. By perfectly filling the space between the casing and the rock, the cement distributes the immense pressure evenly. This makes sure that the rigid steel casing doesn't have to bear the brunt of the load all by itself.
Next up, part 4, crossing the yield point.
Now you might be wondering, what happens when our defenses are pushed past their absolute material limits? What happens when the steel is just asked to do way too much? Well, this is where we run smack into the laws of physics and material science, specifically yield strength. Yield strength is the exact stress level at which the steel permanently changes shape. Think of a rubber band. You can stretch it and it bounces right back, right? That's elastic deformation. But if you pull it way too hard, it warps permanently, or it snaps. When mechanical forces overcome the material properties of our well casing, the steel hits its yield strength.
And the exact threshold we're looking at for industry-standard P110 steel casing is 758 megapascals. To put that wild number into perspective for you, 758 megapascals is equivalent to over 100,000 pounds per square inch of pressure. It's just mind-boggling.
Once the internal or external pressure crosses that 758 megapascal line,
the metal undergoes what engineers call plastic deformation. This is permanent, unrecoverable structural damage. The casing permanently stretches, and then it either snaps open or violently buckles and collapses inward, and at that point, the well is fatally compromised.
Let's look at Section 5, Dynamic Loading and Corrosion.
Even if we safely avoid hitting that yield point instantly, there is this invisible, long-term battle against operational degradation. There are real-time threats constantly testing these material limits. Take dynamic loading, where the system rockets from zero pressure to thousands of psi in mere seconds, sending massive shockwaves through the entire assembly. Then you've got erosion. The fluid being pumped often contains a brace of sand, called proppants, which literally sandblasts the inside of the casing at super high speeds, thinning out the metal. Combine that with chemical corrosion, and you are constantly lowering the pipe's pressure rating over time. This leads to what the industry calls sustained casing pressure, or SCP, where dangerous pressure bleeds into the outer layers of the well.
On top of all of that, we have to account for extreme thermodynamics. I mean, pumping freezing cold hydraulic fluid from the surface down into a boiling hot geological formation causes severe thermal shock. This thermal cycling causes any trapped fluids inside those microscopic cement voids we talked about earlier to rapidly shrink and expand. This constant expanding and contracting physically fatigues the casing and literally tears the cement apart from the inside out.
Finally, Section 6, the Engineering Precision Paradigm.
Let's zoom back out to the control room for a second. As construction and energy professionals know, successfully containing these subterranean forces isn't just about turning on a pump and crossing your fingers. It is overwhelmingly about rigorous, proactive well design. The success of these operations is 90% engineering precision in the planning phase and just 10% execution on the day. You simply cannot out-execute a fundamentally flawed material design when you're dealing with the sheer physics of the Earth's crust. Because the margins are so incredibly tight, modern operations rely heavily on real-time pressure monitoring. By diligently tracking even the smallest drops in sustained casing pressure, engineers can detect potential material failures, like a tiny leak in the casing or a microscopic crack in the cement sheath, long before they ever escalate into a catastrophic collapse or blowout. It really is a constant game of millimeters and micro fluctuations.
When we balance these extreme temperatures, the abrasive dynamic loads tearing at the steel, and the massive geological stresses threatening to crush the wellbore entirely, it leaves us with a pretty profound realization. We are pushing steel, cement, and fluid dynamics to their literal breaking points. It forces us to ask, as our energy needs grow deeper and more complex, how much further can our engineering ingenuity take us before we hit the absolute limits of material science? It's definitely something to think about.